Then just abstractly approaching, I'm going to give you an example they laid out in the exercise and things like that, and to understand this thing. The first example of a motion is this is really a circular motion, not in general motion, and this is a very fundamental and basic motion. It's important foundation for all the other things. All right, here's a perfect disk. I mean, it's a disk. Its shape is the edge is a perfect circle. The circle in mathematics usually means the rim itself. It doesn't really count what's inside in this, like a basketball rim. That object is called a circle. Disk is more of a plate, the whole object, and that's usually the term that we use. So here's a disk, and here's a center, and one way or another that you've seen this motion somewhere in your tire of your car and things like it. So here's a disk, and it's rotating like this, right? That's one circular motion. So when it is moving like that, one thing we consider is how fast it's moving, right? It is not actually moving toward, and the center is fixed. Center is not moving, it's just rotating around it. So there's this idea of, this is example one, idea of a speed is involved in there. Okay? So how fast is it moving, I think it's the most natural notion, it turns out, is actually angular speed. How fast is it rotating? Okay? After 1 second, what is the change of the angle? So I'm going to put this in a different color here, in the red. I'm going to draw the line and put this one point B out there and one point A in the middle. And after a split second later, let's say that was over here. Then you can see B is over there and A is over there. Does that make sense? After a few seconds later, it moved to that direction. But they're always lined up like that because the entire disk moves around together. Does that make sense? Yeah, think about bicycle wheel. You have little reflector on here, reflector on there. Their relative location is always the same, but they stick together and move around like that. All right? So if we just care about what happened to that, you can see that there is this trajectory of the motion. That's A was, if you look at the A, that's the trajectory of A on the disk. And B is following the edge of the disk, right? All right. So you see there's a change of the angle in there? Yeah. So how much the angle speed will be calculated in the following way. All right. How much of the angle that changed it here, this angle theta? Although I use that arrow, dotted arrow there to indicate the distance the point A traveled, but it also gives you an idea about how much the angle changed over time, right? So this is the idea, the change of the angle over what period of time? That is the definition, idea of measuring how fast the angle change, right? If this happened in a short period of time, this is going to be larger. If it's a longer period of time, theta is going to be big. Then you can see the theta, the same amount is divided by a larger number, it becomes smaller. The speed is small, things like that. All right? So we still stick to what kind of measure? Radian measure divided by minute, second, hour, year. If it is really the sun moving around, probably year is a better thing to consider, right? Does that make sense? All right. So that's the idea of angular speed. Angular speed for A and B, which one is faster, is a trick question. After t second, they're lined up like this. For their angles, which one is moving? Angular speed is faster. Angular speed A is faster, or angular speed B is faster, toward to the center. That was the answer, right? Their location and the angle change is exactly the same. So angular speed is the same for A and B, right? Okay. But when people usually think about the speed, is here is that it moved to that much of a distance, not angular, that how many feet did it move at a given time. So let's think about the other usual speed. As opposed to that, they came up with a different term. Usual speed is going to be called here, as opposed to angular speed, linear speed. All right? That's the term they chose. This is about how much of the distance it moves. It's a linear speed of, so let me emphasize the angular speed, the same for A and B. Just what we discussed, right? Discussed. Same for A and B. Make sense? As long as they stick in that spot, it's going to be the same. Now we're going to notice that linear speed is not the same. So I'm going to calculate the linear speed of A and the linear speed of V. They're usually denoted by V in technical terms of physics of velocity, V, and you will use a subscript A to indicate that, how fast it's moving. All right, so that's it. So sorry about this little disorganized manner here. What would be the good notation for angular speed? I think these engineers, these wave analysis people came up with this letter. They use omega. It's a Greek letter. It looks like a W, but it looks a lot like that. It's rounded up like this, omega. All right? So we have two things. Omega A, how fast the angle of that movement on A is changing, and omega B, how much the angle changed for that point B, right? And how do you describe the same for A and B? These two speed is equal to each other. Does that make sense? So that's the observation on the disk. The second one is a linear speed. You have to measure the distance it traveled divided by what? Time required. And here it's a t. So we're kind of assuming there's no jerky motion. It's moving fast and then slow. Not like that. It's just like constant moving around. So the speed is kind of constant. It makes more sense. All right. So what was the idea of the computing the VA linear? Is the distance it traveled. Distance. How much distance it traveled for over time. Right? So A was here. T second later, it was over here, right? Are we going to calculate the straight distance or the actual arc distance? Actual arc distance, right? Does that make sense? So who can calculate the distance it traveled along the arc from here to there? The length of a circular arc, right? Formula of the circular. How did it look like? R times theta. You see the theta is a common for both of the points, but the radius is not. Would you agree? At point A, the radius is different from at the point B. It's larger, right? Big enough. So what would be the good notation for the radius of A? R subscript A. Maybe that seems like a fair notation. So it's a tiny R subscript A. This happened at what period of time? T period of time, right? What would you say if you're just looking at here? We don't need calculation. Just obvious which velocity is faster, which linear speed is faster at B, at A. Given amount of time, which one traveled longer? B traveled longer. So which one is moving faster? No. You have to move faster to go a longer distance in the same given amount of time. I give you 1 second, this guy moved like this. B, in 1 second, he got to move a lot longer, so he must have moved a lot faster, right? So that qualitative idea is clear. Now we're calculating a little bit different in here. So they're calculating, and what about the other linear speed? Is V subscript B, right? How fast is, if it has a speedometer in it, what's the reading in that speedometer, right? So what is VB? Similar idea. The radius for that point would be RB, different from RA, right? Theta, how is it different from theta? Is it half of a theta or 2/3 of a theta? Is the same theta, right? That's exactly the same, divided by time. That's the idea. If you compare these two things, theta and t is the same, RA and RB is different, right? Therefore, we recognize it as different quantity. And something is faster than the other. Does that make sense? Right. So if there's a circular motion like this, there are two speeds involved, angular speed and linear speed. Right? Drawing the picture yourself like this will definitely help you to distinguish these two ideas. And here's formulation algebraically. So here's an important formula. There's an important formula. VA can be reorganized like this. RA times theta over T. Is that all right? Times. And VB is organized like what? RB times theta over T. Is that good? Does anybody know new name for theta over T? We label theta over T something else. What's that? Right, W. Better known as omega. So omega. So VA is now, radius is there times what? Omega. Yeah. Angular speed times radius of the moving object gives you what? Linear speed. Angular speed times radius, linear speed. And this is the idea. How about BV? RB times same omega. Right? So this is the formula. This is how angular speed and linear speed are related algebraically. Make sense? Because these are speed, you use magnitude and make sure you put the correct dimension. So what's the usual dimension of a, speed? We use feet per second. That makes sense? Miles per hour, miles length and hour time, like that. And that came from the formulation of ratio. Length here divided by time. Make good? So that's one fundamental example of circular motion. And there are two notions of angular speed and the linear speed. Think about how the sun is moving around us. If you think about it relatively, if you assume the sun is moving around relatively circular motion, how fast is moving, angle, and if you multiply the distance between these two, Earth and the sun, then you have some idea of how fast it's actually rotating around, things like that. Okay? So those are the one example you're going to see. Second example, then I'm not going to analyze as this much, but we will just use this idea. Linear speed, angular speed is related like this. Second example is a rolling. So here, I was rotating in a positive direction, but I think rolling from left and right is the most comfortable thing to do. This one rotates in a slightly different way, but let's just ignore the sign, just deal with the magnitude. So here is a wheel. Suppose it has a perfect grip, there's no slipping in the motion, it's just rolling toward. And this is a disc, and there's no slipping in between the bottom and the disc. So here's a center, and I have marked point A, and it's going to roll toward to that direction as this one rolling this way, right? Clockwise rotation. Make sense? Right. And I'm going to use this line to help you to and how things are moving. If it's perfectly flat, would you agree if it's rolling to that direction, the center will be exactly in the same height? And here is circle right there, exact same congruent circle. Always there, right? Make sense? Your location of A, is that to the right of the bottom contact or the left of the bottom contact if you move it toward to that direction? Toward the left. Where's A now? To the left or right? Yeah, it's left is the correct amount. Here is your A, the marked point on that disk. Make sense? Now it has, you see this, if you just follow along exactly the center, there's obviously notion of angular speed involved in here, right? Angular speed. Suppose you're looking at the wheel of a car, you're driving exactly the same speed, so you're looking at the center, relatively it's not moving at all. So there's a clear idea about angular speed that you see when you're moving parallel speed. But if you just stop and if you're just watching it here, there's obviously linear motion going on. This wheel is going forward, right? These two are related. These two are related exactly the same manner. Let me explain a little bit more about this is a contact point, right? If there's no slip in and this arc length in here, that's exactly the same arc and length in here. That's the kind of intuition. Would you believe that each contact point to the floor will be, if you put some point in there, you will agree that that straightened up length is exactly the same, the arc length there. So how much it moved to that direction is the same as how much traveled here along the arc. So from there, I hope I will believe that there's angular speed associated to that, and how fast is it moving forward, and that's exactly the same idea in here. The speed of forward motion. Is that all right? But if you really think about, analyze the motion, it's really the same concept. Okay? Any questions so far? Okay. Third example is that this really happens in nature, and you see that, and this rolling thing standing that happen. But third one is quite artificial. It's man-made example, but you see this a lot. Here is gear with all this thing. I don't know what to call this one. I should look it up. And there's this belt, and you see that in a bicycle, or if you look up the hood of your car, there are several belts in the car. So there is something moving, disc moving in a certain direction, and then there's a belt or chain attached to it, and it's it feed in and feed out like that. Usually you don't see that in nature. This happened, this is a man-made situation, but it is quite, I had to do something with this. So if you go to the airport, there is just kind of floor that's moving, so it helps you to, you don't have to walk, you just go that direction. Think about that situation. The floor is actually moving to that direction, just like an exercise machine, and it's actually rolling. It's not going forward. This floor is moving backward. So that's kind of the situation in here, right? So if it is moving in a certain speed, what is a good notion of how fast this disk is moving? What speed is the good to describe that? How fast is it rotating? It's angular speed, right? But nothing is moving in here. But definitely the belt is feed in, and certain amount of belt is feeding out. And after a certain period of time, this amount of length of chain is go inside to that contact, and this amount was popping out from that, and that must be the same amount, right? So how fast this point in here, if you have a market, how fast this point right there on the belt is moving, it is the same as a linear speed, just like the bottom one floor is moving. So is that intuitively clear? The point on the belt, how fast it's moving, is related to this angular speed, how fast it's rotating. What is the formula? That the speed of the point on that belt is related exactly the same as r times omega. What is r here? Radius of that disk that's involved in there. Make sense? These are some of the examples I let out, but I went through. It's fundamentally the same formula is used and things like that. Okay? All right. So here's one example that I think it's called, this part is a crank called Crankshaft, and also have a picture of that. So this is actual, the picture of engine cut out, and when you drive a vehicle, these things, combustion is happening, and this thing is moving. This axle called a crankshaft is in that shape. If you have a full cylinder, they're moving and it's rotating this guy really, really fast. Okay? So how fast is this axle is rotating is a notion of angular speed, right? Correct? Yeah. That angular speed is indicated in your odometer of your car that says 3,000 RPM, 5,000 RPM, 7,000 RPM is a little risky, but that's the notion, right? So when it's moving that fast, they like to use that notion in here. So is described in usually radian per second, radian per minute. Is that all right? How much the angle change per second, how much angle change per minute, per hour, per year, things like that. So that's a mathematically friendly formula here. That's what we wanted to use. But if it is just too much, moving too fast, they wanted to use RPM. This is revolution per minute. Okay? So what does that mean? 3,000 RPM? And 1 minute, how many rotations is rotating 3,000? That doesn't mean your vehicle's wheel is rotating 3,000 times, right? There's a gear mechanism will take that into different rotation. There's different size of gears. Actual angular speed of the tire is different from what you read, but that's the main source of the power, how fast is it rotating there, right? Okay, so that's the one they use. But to calculate, we want this guy, right? So we have to consider revolution per minute converted into radian per minute, right? So how do you change revolution? Let me write it like this. Revolution per minute. Is this notation okay? This is what really the mathematics behind this dimension notation. Per minute means revolution in the numerator, minute in the denominator. That's where that comes from. So how do you change the revolution to radian? Anybody have an idea? One revolution is how many radians? 360, close. We have to use radian measure, right? So that's a 2 pi radian divided by minute. That's right. Yeah, so we don't touch that. So if you see 3,000 RPM, how do you change the radian? 3,000 times 2 pi. So that's the radian measure. So if I say 3,000 times 2 pi, this is way more than 360 degree, right? So we increase this idea angle to this large number so that it correctly reflects the linear motion that is associated with that. Does that make sense? That's the main reason they generalize the notion of angle like that. So we had to spend 2 classes to correctly understand that notion. But here's the nice fit in. You don't have to worry about repeating. Just number itself reflect nicely into the linear. Okay? So enough talking about this, and let's look at problems, right? So here is things that we have discussed. V equal R omega. You know what that is? Right, this relationship between angular and linear speed. So here's an example. Where's the example? That's not the example I wanted. This is example. All right, you saw that, boy, so I'm not going to copy that. Hope you understood the situation. All right. A boy rotates a stone in a 3 feet long sling at the rate of 15 revolutions every 10 seconds. Makes sense, right? Yeah. Find the angular speed and find the velocity of a stone. Angular speed makes sense? The idea. Right? Fast rotating. How about linear velocity of the stone? Velocities? What does that mean by velocities? I don't know. If you have a speed gun and then shoot to to that stone, and what is the reading? That's what the linear velocity is. Does that make sense? Yeah. All right, let's do that together. What is the first thing we should do? Their speed is mentioned in, let's write that down. There's a 3 feet long information. How about rate of 15 revolution every second, 10 seconds? That's another information. So how do you write down the 3 feet long mathematically? What letter do we use? R. See that? Yeah. So if you look at from above, from satellite, they got this picture from satellite. There's a stone rotating from 1,000 miles above. Boom. So you can see that angular speed going on there, right? So, and that is what? That length here? 3 right there. That's why R is 3. Make sense? How do you write the next information? What letter do we use? The Greek letter, right? Oh, omega. Omega, speed, right? How fast is rotating. So how do you do that? Angle measurement divided by how long it took, right? So how much angle measurement is that? 15 revolution. So you keep that like this, 15 revolution. That is certainly amount of angle change, right? Is that okay, 15 revolution? Yeah. How about denominator? 10 seconds. Excellent. Now you set aside these words like this, you know, RV second, and then you simplify this number, right? So what is it? 3 divided by 2. 5 goes in there. 3, 2. Okay? 1.5 revolution per second. Good? But we're not going to use the formula with this measure, right? We're going to change this. How do you change that? Right, convert into radians. So what do we multiply? Pi over 180 or 180 over pi? No. No. Revolution is just 2 pi. Yeah. Right? One revolution is just 2 pi radian. There's no 180. Okay? Remember? This is not degree to radian to degree. It's revolution to radian. So what is one revolution? 2 pi radian per second. Is that okay? All right. So that's the new conversion. So let's do that. And what is this at exact quantity? 3 pi radian per second. Is that okay? 2 cancels. 3 pi radian. So that's roughly like 9 radian. Things like that. All right. So we wrote angular speed in radian per time. Okay. So we answer that angular speed. Find the angular velocities. That's what I mean by that. Angular velocity of the stone. So omega is 3 pi radian per second. It's the exact answer, and you can convert it to 9 point something, but that will be approximate. Any question about angular speed part? Okay. Now, for that linear speed, v, rather than just directly apply then doing the formula, let's think about algebra. What is the linear speed here again? How fast the stone is moving around in here, right? If you have a speed gun and if you shoot toward to that, what is the reading? That's the linear speed, right? There was complicated thoughts involved in there, fairly. Then we want to skip all that, right? How do we skip all that? Using this formula of v equals linear speed is equal to radius times omega, how fast it's rotating. What was radius here? 3 magnitude, 3. And what is the magnitude of angle? 3 pi. Those are the magnitude, right? Now you have to think about linear velocity. What would be the dimension in here? Feet. That's right. That's feet per second. That was the time that we stick to. And we drop the radian, right? Okay. Is that right? So let's say it's 9 pi feet per second. And everybody frowns. Who wants that 9 pi? We usually want how many feet, So let's do that. It's roughly, what is 9 pi in decimal? So let's read the question together again. It's rotating in that speed. Find the angular speed. We did that. Find the linear velocity. We just did that here. So we answer all the questions. Okay? I sometimes forget this too, and you will witness that a lot. But in your test, when you're taking the test, if you build the habit of just reread the question before you move on to, that'll show you that you answer all the questions that was asked in that problem. Any question? Makes sense? Let's do some exercise. All right. First, this is going to be exercise. Let's read this together. Woman is riding a bicycle whose wheels are 26 inches in diameter. If the wheels rotate at 125 revolution per minute RPM, find the speed at which she's traveling in miles per hour. We're going to forget about this miles per hour first. We're going to convert that later. What is natural linear speed coming out of given information, you think here? Forget about miles per hour. Just find the linear speed. What would you preferred dimension of linear speed given the information in this nature? Inch per minute. So we're going to stick to inch per minute, then think about converting it to miles per hour later. All right? So let's focus on inch per minute while we're doing this exercise. So let me give you a little picture. They didn't give you the picture. They're expecting you to be able to come up with this picture and correctly interpret it as one of the examples we went through. And here's a floor, and here is a bicycle wheel in its simplest drawing of the bicycle. And it is what other information do you know about this bicycle wheels? That's right. The wheels are 26 in diameter, right? What do you know about diameter? Isn't that the diameter? Right. So if you just do things in your mind, then maybe your R is going to be 26 and it's wrong, right? But if you draw a picture, you have opportunity to carefully organize and so on. So what do you say about radius? 13, 13, right? So we got that idea. If the wheel rotates, it's not, how much rotation of the sprocket in the bicycle. It's actual how the wheel is rotating. That's the key thing to observe. They gave you that information. How fast this wheel is rotating? 125 revolution per minute. How would you write that right next to it? What letter do we use? Here, R was 13, right? Omega, right? Omega was 125 rev min, right? Rev per min. You write that down. And there's how I find the speed of the bicycle is traveling. So isn't that about the speed of a forward motion? We thought about it, and that uses exactly the same formula. You interpret it as a linear speed and angular speed related. Okay? So from here is your exercise. So please go ahead and do not look at the formula again. It's a very simple formula. Try to remember the formula and try to answer of the speed in terms of inch per minute first, and we'll do the conversion together. Okay, first business you have to take care of is writing omega in terms of radian per minute, right? So 125 revolution change to 2 pi times 125 radian per minute. So if you simplify keeping the pi there, 250 times pi is number, that's the magnitude of angular speed. Okay? Then you use this formula of a linear speed. V is r omega 13, and the angular speed, the radius is given in inch per minute. That's the number. If you actually change the pi to 3.14, it's going to give you roughly how many inches is moved per minute. So that's the gist of it. Last bit is converting this one to something else. Well, I know 60 minutes makes 1 hour. Right now, I don't know how many inches makes a mile, right? If you know that, and then we can easily do that. So I have to look it up, or I have to provide you how many inches makes it 1 mile and things like that. So let's unprepared about this part. I'm going to call the n is the n inches makes a mile. 1 mile. Is that all right? Inches smaller. Maybe it's 3,000. We can find that number in Google. You're Googling 3,000 inches, something like that. But I know this part's easy. 60 minutes make 1 hour, right? So this information, we can convert this one into the correct answer. So here's the 3250 pi. That's the magnitude. And here's 1 inch and 1 minute. Is that okay? Yeah. So how can you change 1 inch to 1 mile? You have to multiply n there, n like that. So n inch is going to be a 1 mile, right? Whatever that n is, you get, let's say it's roughly 3,000. We want to change 1 minute to 1 hour, right? What do you need for that? 60. So you could do 60 and 60. You can't just multiply 60. You have to multiply 60 up there, 60 down there, so that it does not change the quantity. But we can rearrange it so that you can change all the units. That's the principle behind of conversion of all the units. So I'm going to group it. I'm going to group these two, right? And I'm going to group these two so that I can change the units correctly. So here's what happened. 3250 pi. Look at the numerator. 1 inch and times n together becomes 1 miles, right? So I'm going to write 1 mile. How about 1 minute and 60 together? That makes 1 hour, right? Correct? But there are still leftovers. What are the leftovers? 60 is left over there, right? And this n is left over. They're still lingering there. So you put that to the front. 3250 pi times the 60 divided by n, mile per hour. All right? So whatever this number is, n is, let's say, the 3,000. Pi is going to be 3.14, and 60 is 60. If you simplified all that, and that's going to be the miles per hour information to you. Did anybody look that up using the phone? What? 63,360. I mean, did you look up this n? Yeah, what is n?
It's 63,360 inches in a
Oh,
mile.
63,000, roughly like this? Okay, so let's use 63,000 here. So you replace the 63,000 inches in here. That's going to be the number. All right, so let's work this one out. I want you to go ahead and calculate 3250 times pi 3.14. That's pi. 60 divided by 63,000 is roughly how many miles per hour it is it? It seems like 9.6. You have an idea about how slow the 9.6 miles per hour is when you're driving, but if you're rotating like that, that's the forward speed of a bicycle. All right? All right, if you got this 96 miles per hour and then assume that you did something wrong, rotating that, things like that. Always just try to make sense out of it as one way to check your answer if checking your algebra is not first thing you want to do. This problem, once you go through this problem, students have tendencies just to memorize how things work, but like I said in the beginning of the class, that's not what this class is about. I want you to understand a way of thinking of approach this problem, and that's what I wanted to experience. That hey, here's another set of formula. If I memorize it, I can attack this problem in a matter of seconds. That's not what we're doing here. Let's put our thoughts to this one. All right, sprockets and chain of a bicycle are shown in the figure. Okay, so this says 13-inch entire wheel. There's a sprocket 2-inch, it says, and here's a different sprocket. 4-inch, it says in there. The pedal sprocket is this one in here, has radius 4-inch, and the wheel sprocket 2-inch. That explains there. The wheel of a radius is a 13-inch. I think this one has, the wheel of the sprocket 13-inch there. The cyclist, the pedals at 40 RPM. So, how many discs do you see here? I'm going to consider this wheel as a disc, right? Disc 1. What other disc do you see? Little sprocket, you consider that as a separate disc? What about this guy? That's another disc. That's what is involved. I'm going to call that big wheel A, and this one here, disc B. This one there, disc C. And these things are rotated, right? Rotating. So we have a notion of omega A, we have notion of omega B, we have notion of omega C, right? This wheel is rotating here, but what will be the interpretation of a VC, linear speed of a VC? The pedal sprocket is rotating. What is a good interpretation in this context? the meaning of linear speed of disk C. Linear speed of the third example we went through, right? What was that? How fast this chain is moving around. Does that make sense? This rotating creates this chain motion, linear motion, right? How fast is one block of chain is moving in there? That speed is equal to what's linear speed of this one is a linear speed, right? How about this one in here? That one is also rotating. We have a notion of angular speed. But what about the linear speed of the little one in there? Little sprocket. Isn't that just connected to exactly the same feeding mechanism of this chain? So that's the same thing. And how about this big one? It's rotating itself. What is a good interpretation of linear speed of the big wheel? This is strange. What this rotation, it is not really connected to the chain, is it? So you can't say that this linear speed of the big wheel is really how fast the chain is moving. It is not quite connected to here, right? So that's a subtle part. So what is a good interpretation of a linear speed of this wheel? Is a true forward motion of the bicycle, right? So here is the bottom part, and there truly there is a chain. If you look at the bottom floor as like static chain, right? And you are actually riding the bicycle on the exercise machine, and think about this bottom rubber floor is moving around. How fast is the rubber chain down there is moving? That's the linear speed, right? It's down there. This chain in the exercise machine, that's the linear speed. Make sense? That's the situation. All right. What was the key observation is that, we'll go along the way. So let's write down information. Solution together. So let's look at C. Sprocket C. What do you know? Immediate information that is given. Radius R subscript C is 4 inches. What else do we know about this RC? Right, 40 RPM. That's what's given. The cyclist pedals at 40 RPM. This is where the pedal is. So how do you write it concisely? What letter? Omega subscript C is equal to 40 RPM. It's not a complicated number, so why don't we switch right away? How do you switch right away to what we want? 40 times multiplied by 2 pi radian per minute. Is that all right? So let's keep it this way. 80 times pi radian per minute. Is that all right? Perfect. We know everything about this guy. So what about B? What do we know about B? RB is 2 inch. And how about the other one? Omega B, right? Not sure. It's not just given. We're going to figure that out. All right? How about last one? RA? 13 inch. All right. How about omega C? Omega A, I'm sorry. It's not given. We're going to figure that out. That's the situation.
So what does it mean by assuming that the wheel turns at the same rate as the wheel sprocket?
That's a very good point. That's how these disks are related. That's the next thing. So we just look at locally. We look at this disk, try to write down information that's given. The other disk, information given. We want to relate this one to each other, and that information is the key information that is at, right? So this is what's given for individual things, so let's relate it to each other. Motion starts from here. That does not involve these two disks. So we're going to consider the comment he just forgot your name, Forrest. Forrest mentioned later, but let's relate this one. It's related to chain, right? So let's relate that first. Relationship between each other. relationship between what and what? C and B. Is that okay? They're connected by chain. Let's think about that. So R is given, RB and RC is given. All you have to think about is other things. We don't know omega C and omega B, right? But by these two things connected by chain, radius is different. We don't know about omega, and we didn't even consider linear speed, right? Linear speed. So in terms of linear speed, what can you say about linear speed of this one and linear speed of that one? What was the interpretation of the linear speed of this one? How fast? What is moving? Chain is moving, right? If you look at it here, if you look at the left side or right side, the speed of the chain is the same, right? So what do you write here? VC is equal to VB. Because it share the same chain, how fast chain is moving is exactly how fast the linear speed is going to be. That's the connection right there, right? Let's do something about this one, and then we're going to connect this B and A, and they talked about the B and A. They didn't say anything about A and B. Hidden is this connected by chain. So, any idea? Somebody like to come up with it? VC equals VB. These are the informations given about B and C. How do we utilize that into what we have just observed? VC and what does it got to do with R and omega? Right. Multiply them together. VC is RC omega C, right? What about VB? RB and omega B. Okay? This is an equation. See what we know. RC known. Is that right? RB known. Omega B? Not yet. Omega C? Known. So you just solve for omega B, right? Then it's going to tell you that unknown omega B. It's great. Let's do that. RC is 4. R omega? 40 revolution? Not a good idea. 80 pi, right? 80 pi is the one to use. Equals RB, 2 inches, and omega B in radian per minute is what we're looking for. So what do you see? Omega B being 2 times 80 pi, you see that? 160 pi radian per minute. Does that make sense? Yeah, that's what it is. Any question? Okay. So we figure that out. What is the angular speed of a wheel sprocket, which is angular speed of B? And we did that, right? There it is, yeah. That's omega B. So part A is asking, find the angular speed of the wheel sprocket right here. Wheel sprocket is a little one. So that's omega B. And that's 160 pi radian per minute. We answered part A. Any question? The key idea is, what is the key idea, I think? Is come up with this statement right there, you think? And then approach algebraically from that point on, using the formula. That's the key step you need to focus on. Alright, this is the most difficult part to come up with. Alright, let's look at part B. What is it asking? Speed of the bicycle. According to our interpretation, what is a speed of the bicycle? It's the linear speed of this wheel, right? Okay. So we know about all the speeds at the sprocket B, all the speed of the C. It's about how A and B are related, right? Because they're stuck together intuitively, they rotate at exactly the same speed. But they said that in the statement, right? Did they really say it? Yeah, assume that wheel turns at the same rate as wheel sprocket. They're stuck together, right? So how do you write that statement nicely algebraically? What is the same when you look at A and B? Radius is different. Linear speed, I don't know how fast chain is moving versus how fast is moving forward. But something simple. What's that? Omega B, right? But omega C? Omega A, I'm sorry. How are they related? Which one is bigger? Omega A is bigger, right? No. Omega B is bigger. No. They're stuck together. They're rotating exactly the same angular speed. The disk, think about it, doesn't matter A or B, they're rotating exactly the same speed. Remember that? So what goes in between here? Equal symbol. This time is not the linear speed is the same, it's angular speed is the same. Alright? But we already know omega B, right? What's omega B? 160 pi radian per meter. What is it asking? Find the speed of bicycle? How do you write it as a variable? V, right? Linear speed. V subscript A. That's the ideal. What's the next step? RA times omega A. Is that right? What is RA? 13. What is omega A? The same as a little one. 160 pi radian per minute. Not per radian per minute. What should be the right one? This is linear speed now. VA, linear speed, right? So speed always had time in there. Inches. As things are going in inches. So let me have that number. Well, first, let me have that number in decimal. Change pi to 3.14. We got to change that too. That's why I need a calculator. But it's more information to me, inch per second, and I have idea, okay, how fast it's moving, right? So if you divide this one by 60, then I think it's gonna give an idea. So it's not required in here, but let me go further like this. 6531. Here's 1 inch up there, right? Inch. But down there's minute, right? But 1 minute is 60 seconds. You don't have to multiply 60 anything. It's going in a different direction of. So 6531 divided by 60 is going to be inch per second, right? So let me have that. So that, the calculator, you want to have an idea on how fast it's moving. What's that? 108. Got it. Inch per second. That gives us an idea, right? 1 second it moves 108 inch. That's how fast it's moving in this situation, right? So next time when you go to Walmart, do the measurement and tell your friends that how fast it's going to move. Whatever. It's just a joke. One of the tricky example I see in there. And so I did that. And to go through that thought process. So I'm going to do 83. Let's do that together. All right. It'll take less than 20 seconds to save this one. Just bear with me quick and then I continue. 006, January 22nd. All right. Goes the top part. Delete. All right, let's read this question together. What happened to that? That speed of the equator. The Earth rotates about its axis, and here, a bit like this. Here's the Earth, and there's giant stick in the North Pole. And once every 23 hours and 56 minutes and 4 seconds. I didn't know that it's not exactly 24 hours, but it seems like that's what it is. And the radius of the Earth is 39 and 60 miles, and the guy in ancient Greek time also computed this, a similar number there. It's like that. And to find the linear speed of a point in an equator, somewhere down here is a equator, right? Somewhere down there in Brazil, is that right? There is a building in somewhere in Brazil, an equator, and you want to see how fast this one is moving. If you're just looking at from the sun, there is, or from the moon, and there is just it's kind of difficult to find relative position in the space that to correctly measure, but you can look at here at the top of the North Pole, staring right through that, through the satellite, and how fast this guy's moving. Because this guy's not quite moving at all. Linear speed, right? These guys just, they're rotating itself. So from there to there, observing that is probably a good way to look at the speed. How fast, if you have a long-ranging speed gun, you shoot it there, how fast this guy's moving. That's what I'm calculating right here. All right? So you see this disc down there? This disc is called great circle. Just cutting the sphere in this manner. Not top part, going through the center. So that's the disc is rotating inside there. All right? Think you can calculate this? Let's try it. This is your exercise. So first, here's interpretation. Think about this imaginary cut of the Earth along the equator, and you have this disk rotating, and the radius is 3,900 miles. So it's about omega. So think about the motion. What do we know about is, one revolution, and it took 23.9 hours, right? So I put one revolution over time it took. And revolution changed to 2 pi. So that's one formulation. 2 pi divided by 23.9 is the magnitude of angular speed. Then I multiply the angular speed here and get this number. Radius times your angular speed. 1,040 miles per hour. Faster than the speed of sound. Here's a joke.